So we're starting Unit 9 today, and our first lesson is on parametric equations and calculus. So until now, you have been representing a graph by a single equation involving two variables. In this section, you will study situations in which three variables are used to represent a curve in the plane. The third variable we will be introducing is t, called a parameter. So why do we learn about parametric equations? Number one, to figure out the path of things. Number two, to figure out the direction of something as it moves along a curve. And number three, to figure out the exact position at any time. Now, obviously, this is a video, and normally I teach the lesson in class. So you take notes as you feel you need to take notes, because after the video, then you'll be working on a worksheet. So what are parametric equations? So here's the definition. Let x equals x of t and y equals y of t. They will represent two functions of a third variable t called the parameter that are both defined on the same interval I. So then the equations x equals x of t and y equals y of t, where t is in this interval I, they are called parametric equations. And what you're going to see today is the graph of all the points defined by xy, which is x of t, y of t, is called a plane curve. So here we go. We're talking about parametric motion. So a watermelon is placed on a catapult 5 feet above the ground and is launched at a 30-degree angle with an initial velocity of 40 meters per second. Using g, which is the acceleration due to gravity, and this squared landed over there, and it should have been right there, is the path of the watermelon travels along a parabolic path, and it's modeled by the equation and the graph. Here's the equation, here's the graph. So by using parameters, we can show where the watermelon is located at a specific time using the equations x of t equals 20 times t root 3 and y of t equals negative 5t squared plus 20t plus 5. So example 1, we are going to describe the direction and the motion of the watermelon at time t equals 2.5. All right, so here's what we're going to do. We are going to take our two parametric equations, and I'm going to plug in 2.5 in for t. So 20 times, 2.5 times root 3. So what that ends up being, that's, if you multiply all that together, that's approximately 86.603, because I'm going to have to round. But when we plug in 2.5 into the other parametric equation, we get negative 5, 2 squared. And that turns out, there's no rounding at all. That turns out to exactly be 23.75. So let's describe what that means. So as you can see, okay, this would be 100. And as we go up here, this is 15, 25. So what's happening is x of t, that's our horizontal movement. Y of t is our vertical movement. So what's happening is the watermelon, so we're trying to figure out the direction and motion of the watermelon at t equals 2.5. So we're going this way, 86, it's about right there, 0.603, and then from there we're going to go up. I can do this nicely here. So we traveled that way, and then we traveled that way, and so that is where the watermelon will be at time t equals 2.5. So let's talk about what that means. So let's write it out. So the watermelon travels 86.603 meters on the horizontal path and 23.75 meters. Extend my page here. Vertically. So we are using parametric equations to describe the direction and the motion of the watermelon at time t equals 2.5. Example 2. For t greater than or equal to 0, a particle is moving in the xy plane is modeled by the parametric equations given right here. At what time t, or times t, is the particle at rest? Well, let's refresh our memory on what that means. So x prime of t, which is also dx dt, and y prime of t, which another way to write that is dy dt. What's going to happen is we're going to find the time where dx dt and dy dt both equal 0. That will be the t value where the particle is at rest. So the first thing we are going to do is we're going to take derivatives. So 3t squared, and think about it, we're taking a derivative with respect to t, 6t minus 9. And we want to set that equal to 0 because we're trying to figure out what t value is going to make x prime of t, or dx dt, equal to 0. Factoring out of 3, okay, pay attention to what I'm doing. Divide both sides by 3, and now I'm going to factor this. So we have t, 3, 1, the negative goes there. So we're going to get t equals 3 and negative 1. Well, that can't be the case. I'm not going to have a negative time because it says t is greater than or equal to 0. All right, let's change our color, and now let's find y prime of t. So that's 3t squared, and that will be minus, if I bring this 2 in front, those 2's will cancel. And I'm going to factor out a 3, and I get t squared minus 5t plus 6. And oh, I better set that equal to 0 because that's what we're looking for. When y prime of t is equal to 0, the particle is at rest. And if I factor this, I'm going to get t, I have a 6 and a 1, and then negative. That's not right. I needed a 3 and a 2. Back up. Miss Young better figure out her algebra skills here. t, 3 times 2. They both need to be negative. Multiply to a positive 6, add to a negative 5. T is 3. T is 2. So the particle is at rest when t is equal to 3 because both x prime of t and y prime of t are equal to 0. That's why we can't count t equals 2, because x prime of t was not equal to 0 at t equals 2. So what you're looking for is the t value that is the same for both of them when x prime of t and y prime of t both equal 0. So at what time t is the particle at rest? The particle is at rest when t is equal to 3. Moving on. All right. So we've talked about how to find dy dt, how to find dx dt, which are just derivatives with respect to t. But now we're going to we're going to find the parametric form of the derivative. So if we have a smooth curve C, and it's given by these equations listed, then the slope of C at xy is going to be dy dx, and the formula for that will be dy dt over dx dt. And we have to make the assumption that dx dt cannot equal 0. Then the second derivative we're going to also take, we're not going to really focus on the third derivative, but it's mentioned here. So when we go to find a second derivative, that's a derivative of the first derivative. So therefore, we're going to take the derivative with respect to t of dy dx divided by dx dt, and so forth. All right, let's go. Example 3. A curve C is defined by the parametric equations x equals t squared and y equals t to the third minus 3t. We're going to find dx dt, and we're going to find dy dt. So x is t squared, and y is t to the third minus 3t. So we're going to find dx dt, that's 2t, and we're going to find dy dt, which is 3t squared minus 3. Okay, part A is done. Part B, we are going to find dy dx, which is dy dt over dx dt. And if that's confusing you why that's the case, let's think about it. Take the top, which is dy dt, times the reciprocal of the bottom, which is dt dx. They cancel. That's why dy dt over dx dt is dy dx. So let's find it now. All right, dy dx. So I'm going to take dy dt divided by dx dt, and voila, there we go. Pretty basic. Okay, so we found that information over there. Moving on. Part C. Let's find a second derivative. Okay, so let's write this out. We know that that is d over dt. We're going to take... Okay, so let's write this up here so we refresh our memory. Remember, dy dx is going to be 3t squared minus 3 over 2t. So we are going to take a derivative of that dy dx divided by dx dt. Right here, and dx dt, if we recall, let's write that out. We know that dx dt was 2t. Okay, so we have to use the quotient rule. So here we go. We have low d high, so that's 6t, minus high d low, all over, no, all over low. Yes, I was doing that right, exactly. All over that 2t. Oh boy. Okay. So what do we have? We have 12t squared minus 6t squared plus 6 all over 4t squared all over 2t, which is the same thing as multiplying by 1 over 2t. So as a result, we get 12t squared minus 6t squared plus 6 all over 8t to the third. Well, 12t squared minus 6t squared, that is 6t squared plus 6 all over 8t to the third. And if we chose, let's say it's multiple choice, and we were going to reduce, then obviously we can see that we can, if we look here, we have a 6, a 6, and an 8. They're all divisible by 2. So when we divide them all by 2, there we go. So what did we just find? The second derivative. Part D. The curve C has two tangent lines at the point 3, 0, where the curve crosses itself. Find the equations. Okay, so first of all, I'm going to just do a quick little sketch, and I'm going to show you how to use the calculator in just a little bit here. But this is if we graphed our, we have x equals t squared, and we have y equals t to the third minus 3t. If we graph this, I want to kind of show you what this is going to look like. Let's change my color here. It's going to come up like that and go up there. It's hard sometimes to graph it like that, but that's what it's going to look like. All right, so the curve C has two tangent lines at the point. So this is x and this is y. So we have to figure out the t value that's going to result in this happening. So when x is 3, so therefore if you take a square root, we're going to get plus or minus root 3. And here we plug in y, which is 0, factor out a t. So we get t equals 0, and then t squared minus 3 equals 0. So t squared equals 3. So t equals plus or minus root 3. Okay, so what we're looking for is the t's that are the same between the two. So we are not going to use that one because of that. So I'm going to write something right now. So t equals plus or minus root 3 are the only values of t that result in the point 3, 0. So when we're graphing this, think about what we have. We have parametric equations. So we're picking, as we plot this, we're picking different t values to create an x and a y, and that's all these little points. That's how that's where they come from. So now it's asking us, we're going to keep going. So if you think about it right now, no, I'm not quite ready to do that yet. Okay. So we already know that dy dx, which is dy dt over dx dt, is 3t squared minus 3 over 2t. So what are we going to do? Well, we are going to plug in t equals root 3 and t equals negative root 3 and find the slopes so that we can create our tangent lines. So let's do that. So if we plug in root 3 in for t to root 3, we're going to get, that's going to be 6 over 2 root 3, multiply both sides by root 3, and I have to extend my page here, and we're going to get 6 root 3 over 6, because this will turn into a 3 times 2 is 6. So we get root 3. Okay, let's do it again. Now we want to plug in negative root 3 in for t. Whoops. All right, so on top, we still get 9 minus 3, we still get this. Over now a negative 2 root 3 times both sides by root 3. And we get 6 root 3 over negative 6. So we get a negative root 3. So what did we just do? We found out the slopes when t is equal to root 3 and t is equal to negative root 3 at the point 3, 0. So what did we just do? We just created two tangent lines. So let's write them out. Okay, so tangent line number 1. So point slope form. So remember the point we're dealing with is 3, 0. So y minus 0 equals m x minus 3. So y is equal to root 3 x minus 3. And tangent line, whoopsie, tangent line number 1. Tangent line number 2 is going to be y minus 0 equals negative root 3 x minus 3. So we get y equals negative root 3 x minus 3. What did we just do? We just created two tangent lines at the point. The tangent lines are at the point 3, 0. And if you look up at this graph, here is the point 3, 0 right here. And so we have a tangent line right here, and we have a tangent line right there. One is a negative slope and one is a positive slope. All right, example 5. We're going to find all points, if any, of horizontal and vertical tangency to the curve. We're going to use a graphing utility to confirm the results. All right, so here we go. We're going to find dy dx, so that's dy dt over dx dt. So when dy dt is equal to 0, we have created a horizontal tangency. And when dx dt equals 0, we have a vertical tangency. All right, so let's do it right now. We have dy dt is going to be 3t squared minus 3. Factor out a 3. We get this. We're going to obviously set it equal to 0. So t is going to be plus or minus 1. Dx dt is 1. Oh, okay. Well, there's going to be no vertical tangency since dx dt will never equal 0. So now let's go back and focus on our horizontal tangencies. So let's scroll down here. And okay, I'm going to go back and rewrite these so we don't have to scroll up and down. So when t is equal to 1, x is equal to 5, and y is equal to 1 minus 3 is negative 2. So we have a point, 5, negative 2. When t is equal to negative 1, x is going to be 3, and y is going to be 2. So there's our other point, 3, 2. So what did we just find? We have horizontal tangencies at 5, negative 2, and 3, 2. All right, so here's what I want us to do. We're going to check our results by plugging this in our calculator. All right, so I'm going to grab out my calculator right now and open it up. Might take a minute for it to open up. And the key is what you have to do, and maybe my calculator, oh, there it goes. It's just taking a while. We have to change our mode. We have to change our mode to parametric mode. So when my calculator finally opens up and I get it to a big screen, you're going to go to mode and you're going to make sure you're in radian mode, obviously. But instead of function, you're going to arrow over to parametric and you're going to hit enter. Then we're going to go to window, and usually what I do, I like to include some negative values of t unless it specifically says you're not supposed to. And so what it is, remember how these curves are created. We're picking different t values, plugging into the parametric equations to get our x's and y's. So I'm going to randomly just pick negative 3. That seems to work well. And then t max is 3. And now and then my x min, x max, I'm keeping it negative 10, 10, y min, y max, negative 10, 10. Hit graph. And, oh, you can't hit graph until you plug in your parametric equations, Miss Young. Okay, so our first parametric equation is t plus 4. Our second parametric equation is t to the third minus 3t. There we go. Now we can hit graph. And there it is. Now look at that. We just said there's 2 horizontal tangencies. And so the one horizontal tangency is at 5, negative 2. 1, 2, 3, 4, 5. Down negative 2. That is definitely a horizontal tangency right there. The other one's at 3, 2. 1, 2, 3, up 2, and there's the other horizontal tangency right there. So we just confirmed our results, and I can go over that obviously more in class. So next problem is example 6. All right, on example 6, what we are doing is we're determining the t intervals on which the curve is concave up or concave down. So let's grab out our pen again. And I have to find, obviously when it talks about concavity, I need a second derivative. So the first thing I have to do is find a first derivative. And we know that dx dt, because there's is going to be cosine of t. And we know dy dt is going to be negative sine of t. So let's plug those in right here. So we have negative sine of t over cosine of t. There's our first derivative. Well, we have to now do a second derivative, and recall that is taking a derivative with respect to t of our first derivative all over dx dt. So here we go. quotient rule. So we're going to take low d high, which is going to be negative cosine of t, minus high d low, all over low, low, and all over dx dt, which is cosine of t. Let's do some simplifying now. So we're going to have, let's see, negative cosine squared t. It's a positive. That'll be minus sine squared t. Okay, wait. Low d high. This has to go like that. Low d high minus high d low. Yeah, I don't know why I have that bracket there. I don't need this bracket here. Let's take that away. Okay, low d high minus high d low. There we go. Much better. Okay, and now all over cosine squared t divided by this, which is the same thing as multiplying by 1 over cosine of t. And let's keep going. Factor out a negative. Cosine squared t plus sine squared t all over, nope, that's not what I wanted. All over cosine squared t times 1 over cosine t. Cosine squared t plus sine squared t is 1, so we have negative 1 over cosine to the cubed t. Cosine cubed t, where is that going to equal 0? That's going to equal 0 at t equals pi over 2. And remember, we're dealing with an interval that they gave us from 0 to pi. What does this tell us? This tells us that the second derivative, which we just found, does not exist. Okay, in that interval. And at, well, I should say at pi over 2. It does not exist, not in the interval, it does not exist at pi over 2. So now let's do our little number line here. We're going to determine where it's concave up and concave down. So think about what's happening here. At pi over 2, it's where this does not exist. So that means pi over 2 is our inflection point. That's where it's going to change concavity. We're going from 0 to pi. And so if we think about this, if we go back and we look at our second derivative and we think about cosine is positive anywhere between 0 and pi over 2, but we're dealing with a negative of it. So it's going to be negative, and that results looking like that, which is concave down. And from pi over 2 to pi, cosine is always negative, but a negative times a negative is a positive. So that's going to be concave up. And that makes sense at pi over 2 that the second derivative does not exist because that's the inflection point. So now we can summarize by writing this. Concave down and concave up. And now I have 6 AP questions. I will be printing them when I return.